Hi everyone, and welcome to today's webinar, The Infinite World of Spectrophotometers. Presenting today is Tim Mao, our Applications and Technical Support Manager at X-Rite. I'm Robert Grotans, the Global Digital Learning Manager, and I'll be moderating today's webinar. Just a few things to go over before we get started. Due to the number of people that are attending today's webinar, we will keep everyone muted. If you have any questions during this webinar, please use the questions function on the GoToWebinar panel, and we will have some time at the very end of this webinar to answer a few of those. If we don't get to your question, we will also follow up with you after this webinar. Finally, this webinar, along with the Q&A, will be recorded, and you'll receive a link so that you can review the webinar at your convenience. This is usually sent out tomorrow. So with that, I'll turn it over to Tim to get things started.
Thank you, Robert, and welcome everyone. As Robert said, we've got quite a bit of material to go through today, and I want to leave a little time for questions. So let's dive in to what we've called the infinite world of spectrophotometers. So our agenda, we're going to talk about a number of things. First of all, what exactly is that big long word, spectrophotometer? What does it mean? What types of spectrophotometers are there that exist in the world? Do those devices all see color the same as we do as humans? And then ultimately, how do I choose the right device? I'm going to measure something or want to look at and assess the color of something. How do I pick the right device? So we'll go through each of those. Let's start with what is a spectrophotometer. So we're going to actually do a bit of linguistics about that very complex word. It's really three words put together. Spectro, which is, by the way, also accepted as the short name of these devices, kind of like my name is Timothy, and only my parents call me that name, pretty much, right? My shortened name is Tim. Like spectrophotometer, the shortened name is spectral. So if you hear somebody say that, that's typically what they're talking about. But what does spectro mean? Technically, it's a combining form meaning spectrum. That is, it's having to do with specific electromagnetic wavelengths. So it's spectro plus the word photo, which essentially means light, and added to that, the word meter, which is essentially an instrument for measuring. So we could actually look at it backwards and say it's an instrument for measuring light, the wavelengths of light. So why do we need to do that? Because of this. So the top part of that image, you see light shining through a prism and it being split into the various wavelengths of light that give you all those colors, something you probably all did in science class at some point in your life. So those wavelengths, as labeled in the bottom of this image, run from 400 to 700 nanometers. Those are the wavelengths of light that we see. And every color that you see, the reason it's the color that it is because of the wavelengths that it reflects and the wavelengths that it absorbs. So if you're looking at an orange, it's absorbing lots of the 400 to 500 to 550 nanometer waves, and it's reflecting lots of the orange waves out near 600 and 650 and so on. So that's how we see light, or how we see color, is because of that interaction. And so, of course, a spectro, or spectrophotometer, if we're being correct, is measuring the light reflecting at those various wavelengths. That's necessary for us to be able to see. Now, there's light below 400, or there are waves below 400 and there are waves above 700, but we can't see them. The human eye doesn't detect them. So that range, 400 to 700, is called the visible spectrum. So that's a spectrophotometer. Now let's talk about what types there are. And I'm going to talk about two main ways that they vary. There's more than two, but these are the highest level, most important for us. One is their geometry, and we'll spend some time talking about that. And then another is about what's it designed to measure and how does that cause some variation. So let's start with the geometry. And we're going to start first with what's called a 45-0 geometry. And whenever we are looking at the geometry of a device, the first number we get tells us where the light is, and the second number tells us where the detector is. So as you might guess, if I show you kind of a cartoonish kind of drawing of a 45-0 instrument, we've got lamps. Now it's not quite this simple, of course. It's not just a light bulb shining down. There are lenses involved and all kinds of things happening. But as those yellow arrows would indicate, the light is shining on that sample at a 45-degree angle. That's the 45 part of the geometry. The receiver then, which you can think of the receiver like your eye, right? It's the instrument's eye. It's where it sees the light that reflects off of, in this case, this blue sample. And it's going to receive that at 0 degrees or perpendicular to the surface. Hence the geometry 45, 0. So this is one geometry. It's a directional light source shining at a specific angle. Think of it like a spotlight. It's a lamp with a lens that's focusing the light, so we get specific light coming at that 45-degree angle, and our receiver is at 0. An example of that device is the X-Rite MetaView VS3200. It's one of our devices that is this kind of geometry. Let's move on to a second geometry that's typically called sphere. Its correct designation geometrically is D8. Now, we said the first number before the colon is where the light's coming from, but now we've got a letter. And the D stands for diffuse. So as its name sounds, when we generically call these sphere instruments, a sphere device has a hollow white sphere inside of it. And as we're showing in the drawing, we've got a light source that's in there. You see the yellow arrows coming over it, coming out of it. That's the light shining into the sphere, into this hollow ball, if you will. But you'll notice there's a piece of the what's called a baffle that's kind of sitting on the bottom side of the light. That's to prevent the light from being able to shine on the sample, because we don't want any direct illumination here. We want all of it to be diffuse, which is what that D stands for. So the light from the lamp is going to hit the wall of the sphere being a white surface and very diffuse, is going to scatter the light in every direction. And then those beams will bounce all over, and basically the entire sphere becomes a light source and illuminates the sample. So we don't have a directional light source like in 45-0 where we know the angle of the light is coming. Now we have a diffuse light source where we have light coming literally from every angle and hitting the sample. Now 8 in the sphere geometry is 8 degrees from perpendicular, is where the sample measurement is taking place, or again, where you can think of your eye being, viewing that from 8 degrees to perpendicular. Now with a sphere instrument, you'll notice at the bottom here, we explain, or we describe spin or SCI measurement. That's what this sphere is currently set to measure. A sphere can also do what's called an SCE measurement, specular excluded, right? Where we're literally opening up an exclusion port in the device to allow specular light, and I'll tell you more about that in a second, to escape the sphere. We're not going to go in depth into SCI and SCE because that's another half an hour or longer webinar on its own. We have resources on our website to help you with that if you want to dive into it deeper. But let me use this just to describe briefly what we're talking about. This bright white shiny part of this swatch I'm showing you, this blackish swatch I'm showing you, is just the reflection of this light source in there. That's, we call it gloss or specular reflectance, right? It's bouncing off there and I'm not really seeing the color of that object. I'm seeing the reflection of the light. The specular port allows us to let that light that's bouncing off of there because of its gloss or its specular reflectance to stay in the sphere, that's SCI, or to open the sphere and let that light get out, that's SCE. It gives us two different answers, if you will, with a spherical device. Now, some examples, we've got benchtop sphere devices like the CI7800. We've got handheld sphere devices like the CI64. Both of them have the ability to do specular included, specular excluded, and they're using the same basic principles for how they measure color. So that's the second geometry, what we'll call sphere. The third one is we call multi-angle. And if we were to label it with all of its numbers, it would get really long. And so we use multi-angle as a description. But essentially, as you might guess, it's measuring at multiple angles. We have a lamp. Again, it's just like in the 45-0. We have a lamp with a lens shining light at a specified angle, 45 degrees to the sample, right? And then we are measuring. In this case, we're looking at the measurement angles for a 5-angle instrument at 15, 25, 45, 75, and 110. It's obviously for measuring things that change depending upon angle. So think of, the metallic color on your car, which looks different at different angles. That's the reason you would need a device to do this. Now, we have multi-angle instruments that measure 5 angles. We have them that measure 6 angles. We have them that measure 12 angles. If you get a more special effect going on with the surface that you're measuring, you might need more angles to be able to quantify how the color changes depending upon the viewing angle. So you can think of this, again, if you're thinking about your eye like the detector in an instrument, it's like shining a light down on it and then moving your head and looking at it from different angles to see the color. So a multi-angle instrument is literally like, in this case, 5 spectrophotometers in one box. It's measuring at 5 different angles. We'll get 5 sets of reflectance data, 5 sets of color data. If you go to 6 or 12, you get that many sets of data. So an MAT12, like in the lower left-hand corner here, that's a 12-angle device. The MA5QC in the upper right-hand corner here, that's a 5-angle device. Different reasons, different applications why we might need more or less angles, but that's what a multi-angle geometry instrument is like. So we've been through the 3 geometries. There are other differences as well. For example, it comes down to measurement methods. Am I needing to measure reflectance, meaning I'm going to measure the light reflecting from a surface? So here's a picture. I've got a piece of orange plastic. I'm going to measure it with this, happens to be a CI64 sitting on there. It would be shining the light on this as we were just looking at, diffusely from the sphere inside of there and measuring the light that reflected off of it. And we would measure and see that that's orange. But maybe I might also need to measure transmission instead of reflectance. Well, transmission is measuring light passing through the object. So now this is a benchtop sphere instrument, and you can see I'm also measuring an orange, but it's very transparent. And the device is actually the light is here. The detector is on the other side over here. And so we would actually be measuring the light that's passing through it. Maybe that matters to me because I need to measure it, the color of the light that passes through it, the amount of light for opacity or haze. There's a number of different reasons I might need to do a transmission measurement. And in some cases, I might need both. I want to know what color this is from a reflectance perspective, but I also want to know about light passing through it. So I may do reflectance and transmission, but they're different measurements that may require different devices to do their measurements. Likewise, we have what I'm calling static or fixed kind of measurements, right? Like this, right? It's a benchtop device or a handheld device. You're in a laboratory. It could be in a production environment as well. With a handheld device, of course, you can bring the device to the sample versus bring the sample to the device. But you have the ability to do a measurement, do formulations, do quality control, those kinds of things with those kinds of static or fixed kind of measurements. But there's also the ability to do inline. So this is a different spectrum. This one's called the Varicolor spectro. And what you'll notice is that this instrument is not, number one, it's not anywhere close to touching what it's measuring. There's a significant distance between those two things. And in this case, this orangish color you see on here, that's actually on a conveyor and is moving. And so we're doing inline measurement, meaning we are going to measure the product as it's moving underneath, right? And that's a way that you can set up to have this instrument automatically firing at certain intervals every time X amount of feet or inches of product goes by, or every so many seconds or minutes or whatever. You're taking measurements, and of course then you can check for color consistency on a continuous process versus a static or fixed thing where you're doing more like spot checking. So again, another way that we may have different needs, and that may lead us to thinking about a different instrument. Now, let's talk about if they all see the same. So let's consider this single plastic chip, okay, with two different gloss and texture or texture levels. So this is a piece of black plastic. I've had this thing for 20 years or more. I just took a picture of it with my cell phone, so it's not the greatest picture in the world, but you can definitely see it's a single piece of plastic, but it's two very distinctly different colors from the way we look at it now. The one on the top is black, and the one on the bottom we would say is gray, even though we know it's a solid piece of plastic all the same. And the only real difference is the surface, right? The bottom half, the surface is very low gloss or textured, and the top half, the surface is a very high gloss and very smooth. So that looks at this particular angle with my camera like two very different colors. Now, what do we get if we look with a 45-0 or a multi-angle or a sphere in specular excluded? What do they see? If I measured the top, they would get that. And if they measured the bottom, they would get that. Very close to what we see. Okay? Very, very repetitive, very, very accurate depiction of what we see. If I measure them with specular included, with a sphere, that's the top and that's the bottom. Very, very close to one another, right? In specular included, because remember in the sphere with a specular included, I'm closing the door. I'm not letting the gloss escape, and so I'm capturing all the light in all cases. So we won't go into the why of that. Again, that's a very much more in-depth technical discussion. Happy to have that with you. Happy to give you resources for that. But here it's just important for us to understand measuring the exact same thing with different devices, I get different answers. So they're all giving the right answer. And in fact, while you might say, well, in the middle, the 45-0 multi-angle and sphere SCE agree with what I see. If you take this plastic chip and hold it at a different angle and take a picture, I get this, which is what the sphere and SCI sees. So they're both right because it looks different depending on the angle I'm looking at. Let's look at one more example. How do we think the different geometries will see this auto paint? Again, it's a picture I took of a color that goes from being a gold to a blue metallic, depending upon angle. And with a picture, it's hard to get a lot of the angle in here, so we're only looking at a little bit of the variation that occurs in this color. But I took this panel, I measured it with a 45-0 instrument, and it said it's that color. It sees it as a solid color, okay? And I measured it with a sphere, and it didn't really matter whether I used specular included or specular excluded, I got that. Now, you can see visually the 45-0 and the sphere are seeing it as different colors. There's a difference there. And think about it, the 45-0 is measuring it at one angle, right, with a directional light source. The sphere is actually measuring, because it has diffuse light, it's like averaging all the different angles together in some ways. And then if I measure that with a multi-angle 5-angle instrument, I'm going to get that. Those are the colors it sees at those different angles. It's going to start to represent more closely what we see. So again, what product, what is it that you're measuring? What are its properties? Might tell you which instrument is going to agree better with what you see. Now, all of that leads us to choosing the right device. So to start with, the first question's always got to be this: will I be sharing or comparing data in a distributed workflow? the differences in the geometries and the illumination, right? The direct of the 45-0 or the multi-angle versus the diffuse of a sphere mean the data between the geometries is not compatible. Now, a sphere instrument and a 45-0 instrument, both measuring a blue, are going to detect it's blue, but you can't compare one to the other because they will see them differently because of that illumination difference. And so we've got to be concerned about that. If you're in an industry or you're working with a supplier, supply chain, and everybody's measuring with a sphere, you can't go in and say, well, we're just going to measure with a 45-0 or vice versa and be successful, because the data is not going to be compatible. And when we talk about data, we're talking about you can't share standards. Your delta differences might be, your color difference measurements will vary potentially. They can be very close on some samples. They can be very far apart on others. It has to do with how coarse is the texture of the sample and the gloss of the sample and the curvature of the sample, all those things that come into play. Again, it's all because of this direct versus diffuse illumination. The next thing you need to ask about choosing the right devices, are there industry standards, specification, or historical reason for requiring a specific geometry? Standards, are you conforming to ISO, ASTM, DIN, AATCC specifications for what you're measuring? It may require, those specifications may define and require a specific geometry. Obviously, you need to meet that. Some specific indices require a specific geometry. I mentioned earlier, there's a thing called haze measurement. It's a means for measuring with transmission measurements to calculate the clarity or the clearness or haziness, as its name would indicate, of a translucent, transparent plastic. There's a specification that requires a specific geometry to do that. You can't just pick and choose, right? Does the material I'm measuring demand a specific geometry? Kind of like what we were looking at, right? But it can also come down to, do I need to do transmission measurements? That's going to drive me to a specific geometry, because transmission measurements only happen in benchtop devices, not in handheld devices. And that means that you would be using a sphere instrument to do those measurements. Do I have effect finishes like that auto paint where the color changes drastically from one angle to the next? That's probably going to make a determination about what instrument I use. Even the size of the sample. Some instruments can't measure, can only measure down to a fairly large size, right? For example, multi-angle instruments are around 20 to 25 millimeter sample. That's the smallest size they'll go, right? When we go to the MetaView, for example, we can measure a 2 millimeter sample. So the size of what you want to measure or need to measure may also have an impact on the right geometry. Then this question, will the result from a specific geometry more closely match my customer or the consumer's visual assessment? Ultimately, consumers looking at products make buying decisions. Color and appearance are a big part of that. So we want to make sure that we're using the right geometry to match what they're seeing, right? Again, back to the black plastic that I was showing you, right? What does a customer see? I need a device that mimics that, right? That will likely influence my decision. Then, do I need to measure inline or require non-contact measurement? Remember showing you the VS410. We have lots of other devices as well that will measure what we call inline, are doing that continuous measurement of product as it's moving by. Some of them even scan across from side to side. We measure everything from carpet to siding to extruded plastics and those kinds of things with these inline non-contact measurement devices. And consider the fact that there's the possibility you might need more than one type of instrument geometry, because you might have different needs in the products you're producing where you say, I need this geometry to do this part properly, but we also have this new project, we're developing a new product, whatever, that's got a new kind of finish on it or a new kind of challenge, and might mean we need a second instrument to do measurements for that. All of those things need to come into the decision to help you determine what's the right device. So that was our agenda. We went through what is a spectrophotometer, what types there are, how they see color, and the things to consider to choose the right device. With that, we'll move on to the Q&A. I know we've used up most of our time, but we'll try and answer a couple of questions here, as well as the resources on the screen here, www.xrite.com. You can go there and get access to other webinars we've done in the past where we cover some of these other things like spin and specular included, specular excluded, and those kinds of items. So let's go to questions, Robert.
Great, thank you, Tim. I see a few questions already. If you haven't submitted one, please feel free to do so. I am going to launch another polling question if you'd like to talk to someone one-on-one as well. So let's see. First question, can you please explain what D65/10 spin means? If you were to see like that nomenclature.
Yep. So that's very typical when you're looking at color measurement data, whether you're looking at LABs or delta E's or color differences. So the instrument measures reflectance, but ultimately we need to calculate what the color looks like under a specific light, because different lights make color look different. So you'll always have something like D65. That D65 is the illuminant. That would be a mathematical representation of a light source. So it's mathematically mimicking daylight. So that's what the D65 means. The /10 means it's using the 10-degree observer values. That's a test that was done to account for human vision. So D6510 is accounting for the light source and the human part in the calculations. And then spin is specular included, or SCI. It's saying that's the mode the instrument was in. Remember, with the black plastic, that's the one that didn't see much difference between the two. If you think about it, if you were formulating that piece of plastic, you want to make sure you got the formula right, the mixture of colorants in it to make that plastic plaque the correct color. Specular included, or SCI, would tell you that yes, you've got it colored correctly, but if it looks very different, it might be because of a surface or an appearance difference. It's not a formulation problem. So that's what D6510 spin is telling you that.
We'll take a couple more questions. Do the benchtops have D8 and 45-0 capabilities?
No, they do not. The benchtop devices are all D8. They're all sphere instruments. It would be possible to build for there to be a 45-0 benchtop device, but there just isn't the need for the most part. One of the advantages of the 45-0 devices is that because it's a directional light source, it is easier to do smaller spots and so forth. It's one of the reasons why I didn't show you, we have handheld 45-0 devices. The MetaView that I showed you is more of like a countertop kind of device, but the handheld instruments get used in the printing world a lot, right? Because printers have to measure very, very small spots, and 45-0 instruments do that really well.
Let's see. Could we expect the inline spectro to read similar to a handheld spectro, such as the CI62?
So for the most part, likely not, because the handheld instrument, the CI62, is a sphere-based instrument. The non-contact devices that are used inline are directional devices. The VS, the Vericolor Spectro that I showed, for example, is actually a 40 or a 30-0, it's not even a 45, it's a different angle. And you have to do things a bit differently when you're in line because of the distances that the instrument has to be away from the sample, and the yeah, it's mostly about the distance, and the non-contact part of it will cause that to be a different angle. So it's a great question. What most often is happening, the way those things are used is they're using, customers are using a laboratory type device, right? It could be a laboratory copy, or same instruments they're using online. They might be using, you can use them in a laboratory in a static fashion. So that Varicolor Spectro, you could have it on a stand in a lab and be measuring with that as well. Or you might be using a sphere instrument to measure in a lab and getting your color okay. Hey, yep, we're ready to run. Now you start running, and what you're doing online or inline measurement is very often about take a measurement at the beginning of the run and then just make sure that it doesn't vary. Because if I know the color is right when I start, I validate in the lab. Okay, color's good. We're ready to run. We start running. Now I'm measuring every 30 seconds to make sure I don't vary, and that works successfully. So it's a combination of things that we have to bring together.
Perfect. We're actually over time now, so I think we'll end here for today. I do see some specific questions with people asking about their applications. I will give those to Tim, and we'll do our best to follow up with you this week. So we will answer those questions. But for today, we're going to stop here. Again, a recording of this presentation will be sent out tomorrow, so you can watch it again. So look forward to that. So with that, everyone, thanks for joining, and have a great rest of your day.
Thank you.